Rafna.
Yeah. So let me just, yeah, the recording is started. I'll just share the screen. Okay, so I guess the screen should be visible now. Um, okay, so yeah, let's start the class. I would like to just give a brief recap and summarize what we did yesterday before we move on to a new topic. So yeah, yesterday's class, like we had a lot of interactions and that was very good. And so I thought there's a need to, just, consolidate whatever we discussed. So what we were looking at was the separating hyperplane theorem. So it said that for two convex sets in Rn that don't intersect, you can always find a hyperplane which separates the two. Okay, and so the way we did this was, we considered a specific example of closed and bounded sets, which are called compact sets, and we did the proof for this case. Okay, so in particular, what we did was we were trying to construct a hyperplane. Okay, and the idea was to show that this hyperplane is, separates the two. And to construct the hyperplane, we looked at this problem where you looked at, the 2 points in the sets C and D, which are sort of closest to each other, and that was used to construct the hyperplane. So basically, to get these coefficients, and then the task was to show that this is indeed a separating hyperplane. Okay, and for that, what we did was, we tried to do it by contradiction. We supposed that, there is a point in D which violates this. Okay, so the claim was this is greater than or equal to B. So this lies on D lies on this side of the hyperplane, and by contradiction, we assume that there's a point which doesn't satisfy this. So in some sense, it lies somewhere on this side, and we derived some sort of an inequality here, which had to hold if the tilde was violating this constraint. Okay, and then we went back and showed that if it indeed if it doesn't satisfy this, then this point D is not the min. In fact, there must be some other point. So this was the idea that came up from all the interactions. So you must have something else which is closer, some other point which is closer. Okay, and yeah, I think there's a typo here, a small typo in this descent direction. So when I was just going through it again, I realized okay, so this had to be strictly less than 0. So anyway, what we did is we produced a descent direction for this function finally, and okay, so then so that was the contradiction that came up. Okay, and we also discussed like why convexity is important here. So there was one question that Siddharth asked me, so which is going to prompt what I think should be told now. So it's about whether convexity is key, or you can have some notion of local convexity. Is that not sufficient? So so I felt that I should clarify one point here, and it's kind of hidden when I talked of this theorem. So what this is saying is that if you have these convex sets, then you have a separating hyperplane. So this is not the only case in which you have a separating hyperplane. So you can have some non-convex regions as well. Even in that case, sometimes you can have a separating hyperplane. Example, so this is kind of like what Siddharth would have suggested. So something like one of the sets is convex and the other one is convex here, but maybe you have some non-convexity here. Still, you have some separating hyperplane here. Okay, so you could construct non-convex sets which still can be separated, but you cannot always guarantee this. But whereas if you have two convex sets which are disjoint, then indeed you can say that there is going to be a hyperplane which separates the two. Okay, so yeah, so I just thought I should state this explicitly. And of course, another takeaway from yesterday's class, which is non-technical, is yeah, there's so much interactions that happen, and I'm sure that helped to clarify many things and get more intuition. So yeah, so for this reason, so I would urge you guys to keep interacting, and any perspectives you have on things we discussed, do share with everybody else as well. Okay, so okay, so we saw this thing about two convex sets, and the final thing we saw in the last class was, now suppose you take one convex set which is also closed. Okay, and here the closed is essential, and you take a point x which does not belong to this convex set. Then in this case, you can have strict separation through a hyperplane. Okay, so for this other case where you have the two sets are convex and they're disjoint, and in this case, the strict separation is not. I mean, this you cannot guarantee this always. So there are examples where this doesn't hold true. So there's one example that we kind of, okay, I think it, okay, for some reason it's gotten deleted, I guess. So there were some examples that we saw to illustrate this idea. So strict separation, to do that you need something more, and here it is a case of the convex set being closed. Okay, that ensures that you can strictly separate the set and the point. Okay, so today what we'll do is we'll discuss an application of the separating hyperplane in yet another theorem called the Ferkus Lemma. Okay, so yeah, this Farkas lemma is also one of the foundational results in optimization, and you will see it getting used in later in linear programs as well. Okay, so in general, the separating hyperplane theorem idea is quite an important one, and in fact, the idea of separation, okay, separating two sets, that gets used in a lot of places. And an example is also in the case of machine learning, right? So when you're trying to build a classifier, okay, which separates, I mean, in true sense, it's something which separates two classes of points. Okay, so if you have some hyperplane, which, if the points are separable in some sense, then it makes life easier. Okay, so it's not directly a separating hyperplane theorem that comes in, but some notions of separation that play a role in many places. Okay, so now let's move on to Ferkus lemma. So before that, were there any questions so far with the last class? I hope things got cleared. Okay,
Yes,
so I think if it was clear to you all, so let's get into Ferkus lemma. So the statement is this. Okay, so suppose you have a matrix A, which is in M cross N, okay, and a vector B, which lies in Rm. Okay, so now what we are saying is exactly one of the following two systems is feasible. Okay, so one system is this one, the set of all solutions to Ax equals B, where x's are non-negative, and the other system is the solution. So this is something where you're looking for an element in Rm. Okay, and A transpose Y less than or equal to 0 and B transpose Y greater than 0. Okay, so these are two systems, and the claim is that exactly one of them is feasible. So for this reason, this is also called the theorem of alternatives. Okay, or it's also called Ferkus lemma. Okay, so let's just try to understand what this means. Okay, it's just a whole lot of notations and matrices and vectors. What does it mean? Okay, so let's look at this first system. So x in Rn such that Ax equals B with x non-negative. Okay, so x is a vector in Rn basically. So if you represent A with these columns, so A1, A2 up to An, these are the columns of A. Okay, so what you're looking for is some combination of these A1 to An, which gives you B. Okay, and it's a special combination in the sense that you want this to be true. Okay, so the x's have to be greater than or equal to 0. So it's a non-negative combination of these vectors. It's not any linear combination. Okay, so that's the idea I want to convey here. Okay, so now this kind of combinations, it's closely related to what is called a cone. Okay, so it's actually called a conic combination. So let's just see what a cone is. So a set S, okay, it's a cone. It's called a cone. If any vector you take, then if you scale it by some positive number or some non-negative number, then even that new number here or this new vector here is going to belong to S. Okay, so that is what is a cone. Okay, so so in a simple example, if you take, so suppose there's just a single point, I mean single vector here A, or let's call this X. Okay, so now if you want to construct a cone from it, what you do is you take all positive multiples of this vector. Okay, so basically you'll have this whole ray, okay, which starts from 0. Okay, so this is going to be the cone. Okay, that cone containing this single vector x. Okay, so yeah, so these cones are also like are objects in optimization. You can have many optimization problems where the feasible set is a cone. Okay, so so here what we are saying is that these x1 to xn are all positive, okay, or non-negative basically. So this kind of a combination, okay, so some combination of non-negative multiples of these vectors, that's called a conic combination of a1 to an. And in fact, if you take the like the set of all I mean written it here, so the set of all such entries, the set of all such vectors which you can represent as a conic combination, okay, that's called the cone spanned by these vectors. Okay, it's also called the conic hull. Okay, so like we had convex hulls, this is a conic hull. Okay, so what they're saying by this statement here, okay, is that B lies in this cone spanned by these vectors a1 to an. So to show it pictorially, so suppose a1 to an, okay, so a1 to an are some vectors. Now if you look at all everything that you can write as a positive combination of these, it will basically be everything in this whole space. Okay, it's of course an infinite space. So basically these are going to be the bounding points, and all the vectors in this whole space are going to be in the conic hull. Okay, so this is the cone span by a1 to an. Now what we're saying here is B is a member of this cone. Okay, so that's what this representation means. Okay, so the first system is telling you that B lies in the cone spanned by a1 to an. Okay, so is that clear? Are there any questions on the cone and the idea of cones?
Yeah, no.
Can you
Okay,
please explain cone span again?
the cone span. Okay, so you remember like a span of vectors. Like if you just say a span of vectors, what would you do? Okay, you would take all possible linear combinations, right? So let me just write that. So if you take a linear combination of a1 to an, so this is just going to be something of this form, right? Some alpha I ai equals 1 to n, where alphas can be anything in the real line. Okay, so this is a linear combination, and if you look at just give me a second. Okay. Okay, I'm bad at this. Fine. Okay, so so linear combination means you're taking any possible combination. I mean, there's no restriction on these signs, right? So basically, you're getting when you do this, and if you let alpha take any value in R, so what you're going to get is a subspace. So this set, right? So the set of all values summation alpha ai for all alpha is in R. So this is going to be a subspace, right? But so if you have this additional restriction that alphas are greater than or equal to 0, they're non-negative, then what you're going to get is a different object. So it is something which is again spanned by these a1 to an, but that object is called a cone. Okay, so basically everything of this form, summation alpha ai, such that alpha I is greater than or equal to 0. Okay, so this is going to be, this is what is called a cone spanned by A1 to AN. Okay, so the difference is if you look at subspaces, okay, the subspace spanned by A1 to AN, what you would have is you would also have some things here, right? So if you take A1, you can have a negative scaling also, right? So you can have minus A1 is also there, and any negative multiple also will belong to that subspace. But the difference is that in conic combinations, you can't have a negative multiple. So all that you have is a positive multiple, and that's why it's sort of this region spanned in between these A1 to AN, and strictly bounded by these regions. Okay, so that is what we will call as the conic hull, or the cone spanned by A1 to AN. Okay, I hope it's clear.
Yes, ma'am, it's
Shivam?
clear. Yes, ma'am, it's clear.
Okay, 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 fine, thanks. Yeah, so so I think I did something and it messed up, but okay, if x element of S and alpha x is also in S, I think that's what it is. Okay, so yeah, so this is the idea of cones and the cone span by them. So this system is just telling you, like, because of this x greater than or equal to 0, B lies in the cone spanned by the column vectors. So that is the first system. Okay, now let's just get an idea of what this second system means. Okay, so let's take a new page. Okay, so the second system is what? Basically the set of all y's in Rn such that A transpose y is less than or equal to 0 and B transpose y is strictly greater than 0. Okay, so this is the second system. So again, if you write, so now instead of, earlier we wrote A as these columns. Okay, so now A transpose is just going to be the same vectors A1 to AN, but written in a row form, right? So something of this form, A2. So this is going to be A1 transpose, A2 transpose, up to AN. Okay, so this is going to be actually A transpose, right? And so A transpose is what? It's an Rn cross M. Okay, so that's basically this, the same vectors here that you took, the column vectors, but you just write it in a row form, and that's what is A transpose. Okay, and now this transpose Y is less than 0. So Y is something like Y1 to Ym. Okay, so that's why Y is in Rm. So this is less than or equal to 0, and B transpose Y is greater than 0. So if you look at this, so if you look at each of them, right? So A1 transpose Y1, so this means A1 transpose Y1 less than or equal to 0. A2, sorry, not Y1, what am I writing? A1 transpose Y less than or equal to 0. A2 transpose Y less than or equal to 0, and so on up to AN transpose Y is less than or equal to 0. Okay, so this, you can recognize this immediately as a set of hyperplanes, right? So if you have, yeah, okay. So A1 up to say some AN. So these are the vectors. Okay, and so let me just finish this. So and now B transpose Y is greater than 0. So Y is something which is giving you some sort of a hyperplane where A1 to AN, these all lie on one side. Okay, so this is say Y. This is the hyperplane Y. Okay, so something like Y. So all points here is Y transpose X equals 0. Okay, and B lies on the other side. Okay, so that's what this system is, right? So A1 to AN lie on one side and B lies on the other side of this hyperplane. Okay, so now if you just look at these two systems, right? So one side you had, like, B was on this side, it was in the span of A1 to AN. Now on the other hand, you have B is on the other side, it will not be on the same side. Okay, so intuitively this is, only one of them can happen, right? You cannot have B lying on some other side, that is, it's not in the span of A1 to AN. It lies on the other side, and you cannot have, if it satisfies this, you cannot have that B lies in the span also. So that's what this theorem of alternatives says. So is this idea clear, the intuitions of what these systems represent?
Yes, ma'am. Ma'am,
Okay.
ma'am, I didn't understand why all the AIs will lie on the same side. I mean, the AN and A1 can also create like obtuse angles, right? So there is no plane between them.
So A, okay. So now the thing is A, okay, so with Y, they should have obtuse angles, right? So let me, okay, so with A1 transpose Y is less than 0, so you have some obtuse angle. Yeah, I mean, they can, uh, yeah, basically, so if is, okay, so what you will get by this half space, right? So in general, like if you have, this is going to be a hyperplane where everything here is going to be x transpose y equal to 0, right? So that point you understand. Okay. Now, anything you take on one side, you will either have it as less than or equal to 0 or greater than or equal to 0, right? So that's where these will lie on, I mean, with respect to the hyperplane, they will lie only on one side, right? Because this, so basically you get two half spaces. This hyperplane divides the entire region into two halves. Okay, so you can maybe try to verify this. So basically y would be something of this form, right? So that's the normal that we have. Okay, and yeah, so A1 to AN, these are like different points here. Okay, and the angle they make with this y is something which is less than or equal to 0. Okay, so it's just the idea of half spaces basically. Like this is something which probably we might have seen this earlier. So if you have, let's just take another thing. So A transpose X equals 0. So we said that, you know, it is, or let's just say A transpose X equal to some B. Okay, and if you take any point on this side, it would have A transpose X as, suppose A is this vector, you will have A transpose X is greater than or equal to B, and anything on this side would be A transpose X is less than or equal to B. Is this idea clear? Like, I mean, forget about these A1 to AN vectors, but if you just take a hyperplane, and is this idea clear about these two half spaces?
Yes, ma'am. Yes, ma'am.
Okay, so now instead of this b, this value b, we are just saying that this is a value 0. Okay, and so that's why you have all these a1 to an on one side, and this b, with respect to this equation, you have this as on the other side. Okay? So yeah, that's the idea behind this system. Okay, so
Also, ma'am, I may be wrong
that,
here, but Nitish's point was that what if there's an obtuse angle, that is all the A1 to AN cannot be on the same side of the hyperplane. If I could be wrong here, but if that is the case, then I think the first scenario becomes true, that if that some of the ANs are on the other side of the hyperplane and you cannot achieve such a hyperplane where they're on the same side, then B will lie in the cone of all the A's.
cone span by 10. Yeah. So that's exactly the idea behind the Farkas lemma. So suppose this, yeah, you, I mean, so what this is telling you is, you know, if you cannot have such a hyperplane where, A's are on one side and B's are on another side, if you cannot achieve this, then of course it must be that, B's are also on the same side of the hyperplane. And in particular, B's lie in the cone span. Okay, so yeah, so that's the idea behind the Farkas lemma. So maybe let's just see a formal proof of this. Okay, so it's not too complicated. It's a simple idea. It's an extension of the separating hyperplane theorem. Okay, so one thing is this cone spanned by A1 to AN, right? So that is actually a convex set. Okay, So in general, cones need not be convex. You can have very non-convex objects. But in this particular case, if you take a set of n vectors and you take a cone spanned by them, that is always going to be a convex set. Okay, so you can try to prove this. Okay, so then it's just the idea of separating, I mean, A1 to AN lie in one set, and then you're looking at a convex set containing these A1 to AN, and B lies either in that set or outside. So if it lies outside, then there's a separating hyperplane. That's the idea. So let's just go to a formal proof. So suppose you take that the first system is feasible. So there is an x which is greater than or equal to 0 such that ax is b. Okay, so b lies in the cone of a1 to an. And now suppose the second system is also feasible. So you have something like this. So there is some y. Indeed, there's a y which A transpose y is less than or equal to 0, and B transpose y is strictly greater than 0. Okay, so now what's going to happen is, I mean, it's just a matter of substitution. So this B is actually AX. Okay, so what this is going to give you is there is a y such that A transpose y is less than or equal to 0, and X transpose A transpose y is strictly greater than 0. Okay, so that's what this is telling you. And of course, we assume that X is greater than or equal to 0. Okay, so that's what these two put together give you something like this. Now, this cannot happen, right? Because A transpose y, so this is a vector, and all the entries are less than or equal to 0. Okay, and now you have X, this particular vector has all entries is greater than or equal to 0. And A transpose y, this vector has all entries less than or equal to 0. So it's something like this, right? Xi times A transpose y, the ith element of A transpose y. So these are all greater than 0, greater than or equal to 0, and this is less than or equal to 0. So this overall summation greater than 0, this cannot happen. Right? So that's a contradiction, and that's why you cannot have these two. If one is feasible, then two cannot be feasible. Okay, this system cannot be feasible. Okay, so now let's assume the other way. So suppose one is an infeasible system. So this part of this proof is the easier part. Like we didn't make use of any the separating hyperplane theorem, one thing. But now suppose let's say one is infeasible. Okay, so that means there is no x in this such that this is satisfied. Okay, so the set x such that ax equals b, x greater than or equal to 0. This is an empty set. Okay, so what is it telling you? That b doesn't lie in the cone spanned by a1 to an. Okay, so b lies outside this set. So basically, this is the set of interest. It's the set of all positive or non-negative combinations of the vectors a1 to an. Okay, and this is a convex set and it's closed, and B does not lie in this set. Okay, so you can use this variant that we discussed in the end. So you have a point here. So B is a vector. You can view it as a point which does not belong to this closed convex set. Okay, so then immediately you have that there is a hyperplane which separates B from this set. Okay, and in this case we saw that the separation is strict. Okay, and so what it means is that there is a y and r. So these are what define the hyperplane. Okay, so you have so you have this y, this vector y and some r, such that y transpose z. So you take any z in this cone, you have y transpose z is going to be less than or equal to r. And if you take B, you have y transpose B is going to be greater than R. Okay, strictly greater than R. Okay, so now the claim is that this R, so this is a hyperplane, but what we had here was something stronger, right? That you had A transpose Y less than or equal to 0. So this R, the claim was, you can have a hyperplane such that this R is 0. Okay, so so let's try to see that. So one thing is, if you look at this cone, this set C, now alphas have to be greater than or equal to 0. So immediately the 0 vector belongs to the set. Okay. So 0 vector belongs to this set. So now if you substitute z as 0 here, so you're going to get r is greater than or equal to 0. Okay, so this has now, so now we have ensured that r cannot be negative, right? So it has to be greater than or equal to 0. Okay, now what remains is, is can we have r as greater than 0? Okay, so that is something we'll check. Okay, so before that, till here is it fine? Are there any questions of the proof till this point? Okay, you're all quiet. It's afternoon and I'm doing something very algebraic, but yeah, but please pay attention. It's not a very difficult proof. I mean, if you just follow it systematically, it's should be easy to follow. So please stop me, okay, if something is not clear. Okay. Okay, I need some response.
Yes, ma'am. Clear.
Okay. Okay. That's going to do. Okay, what about the others? Okay, it's pin drop silence. Okay, let me do this. Let me try to finish this and again come back and we can just go over this systematically and see if there are more questions. Okay, so at this point, what we said is, this hyperplane we construct. We say that there's a hyperplane which separates this point B from this set, from this cone. And, and we said that this R, this particular value has to be greater than or equal to 0. Okay. Now, suppose R is strictly greater than 0, then what's going to happen? So the claim is that, this is not going to happen and R has to be equal to 0. But let's just see what happens. Suppose R is greater than 0. So let R greater than 0. So that means what you have. So what we're trying to say here is there is some element here such that Y transpose Z. Okay, there's some particular Z. So let's just call it Z tilde. There is some Z tilde such that Y transpose Z tilde is greater than 0 but less than or equal to R. Okay, because if it was negative, I mean that we have already taken care of. So let's say it is on the other side of 0 but it's less than or equal to R. So this, it's a positive quantity. So then what you could do is, this is a cone. So if you take some alpha times Z, okay, so I wrote it with these notations. So if Z, so since Z tilde lies in this cone, so alpha times Z tilde will also lie in this cone, right? So how much ever large you take the value of alpha, this is going to lie in this cone, okay? And so then if you try to take Y transpose alpha Z tilde, okay, so this is going to give alpha times Y transpose Z tilde. And this is some finite value which is less than or equal to R. Okay, but now if you take a very large value of alpha, this number, this quantity can become very huge. Okay, for example, let's say Y transpose Z is say some value of 5 and let's say R is 6. Okay, now if you take 2 times Z, even for 2 times Z tilde if you take, you're going to get this value. Say alpha is 2. If you do that, this is going to give you some value of 10. But this is not going to be less than 6, right? So that's so this cannot happen, and that's why you need R to be exactly equal to 0. Okay? So so that's why exactly this happens, and so if this set is empty, then you must have a hyperplane which separates the two sets, and in short, what you're going to have is this system. Okay, so Y transpose Z less than 0 for all R. I mean, for all Z in this C. Now, this cone is just basically this summation alpha AI. Okay, so in particular, if you take Z as all the AIs, so Y transpose A1 is less than or equal to R, Y transpose A2 is less than or equal to R, and so on up to Y transpose AN is less than or equal to R. Okay, and B transpose Y is greater than R. So this is exactly the system that we started off with, that A transpose Y is less than or equal to 0. Okay, so yeah, those are the two pieces of the Farkas lemma. So, okay, so you're all very silent, so you have to tell me what is bothering you.
We'll probably have to go through the proof by ourselves, and then I think it will become more clear.
Okay, but is there some step which, you know, the flow of directions or something which
No,
is
no, no.
unclear? So yeah,
That is clear, ma'am.
okay,
Can
okay.
we go over r equal to how is r equal to 0 again?
Yeah, sure. So you understand till this point, right? Like we have r greater than or equal to 0. Up to this, is it okay? Siddharth?
Uh, no, ma'am.
Okay, so let me know which, I mean, let me start from the beginning itself. So is this first direction clear? So one is a feasible set. So now if you assume 2 is also feasible, uh, you get a contradiction, right? So is this part clear?
Yes, ma'am.
This is clear. Okay. So now let's look at the other part. So the claim is that exactly one of these two systems is feasible, right? So now, so we show that if one is feasible, then two is infeasible. Two cannot be feasible. So now now the other way. Let's suppose one is an infeasible system. So there is no X such that this relation is true. Okay. So this is an infeasible system. So basically this set is empty. Okay, so now we are trying to see whether this other system, the second system here, whether this is feasible or not. Okay, so so to do that, so that's where we use this idea of conic combinations, and in particular this set. Okay, so if you what we have here is B does not lie in this combination, this cone basically. Okay, so the particular set, the cone that we're looking at, is the set of all non-negative combinations of the vectors, of the column vectors of A. So is this clear? This is correspond. These two sets are actually the same.
Yes, ma'am.
Okay, so okay, so yeah, so we are saying that B does not belong to this set. Okay, so now this is actually a convex set. It's a closed convex set. So this you have to see for yourself. Okay, try proving that it's closed and it's convex. Okay, so now because of that, you have a set which is closed and convex, and you have a point which does not lie in this set. Okay, so something like you have this cone. So this is a huge object. Okay, and you have some point here. Okay, so now there's a hyperplane which separates the two. Okay, so we are just invoking the separating hyperplane theorem, and in fact the separation is strict. Okay, so now let me call y and r. Okay, so these are the two quantities. So y is a vector. Okay, so this is a vector and r is a scalar quantity, and those define the hyperplane. Okay, so this hyperplane is something of this form, like y transpose x equal to r. Okay, now what we are saying is that this is a separating hyperplane. So for everything in this cone, we have y transpose z is less than or equal to r, where z is any point in this cone. So this is the cone and z is some point here. Okay, so for all of these, you have the dot product with y. Okay, that is going to be less than or equal to r. Now B is lying on this side, so you have y transpose B is greater than r. Okay, right? So now in particular, since all these vectors a1 to an, okay, so these are all belonging to this cone. So that's the cone we started off with, remember? So this was a cone spanned by a1 to an. Okay, and so that's exactly this cone. So you have a1 and so on up to an. Okay, so Okay, so now all these are part of the cone. So you have in particular that y transpose A1 is less than or equal to R. I'm just substituting Z equals A1 to AN here. Okay, so that's what this is telling you. Okay, now the thing is, we have a stronger thing to prove that R is equal to 0. That's the claim of Ferkus Lemma. So to see that, R, let's just see what, whether R can be less than 0. Okay. So for that, you see that this is a cone in which, if you change these values of alpha, the scalar coefficients, with which you multiply the vectors, then you'll get different elements. So in particular, if you put alpha is as 0, you will get that 0 belongs to this set, right? Just set alpha is as 0, so you have the 0 vector, and that belongs to this cone. And you also have this is true. Okay. So y transpose z is less than or equal to r for everything in the cone. So now if you substitute z equals 0, the 0 vector, what you're going to get is something like this, right? So r is greater than y transpose z, and this z is, instead of z, we are taking 0. So this is actually summation yi zi, okay, and zi's are all 0. So that's why you will have r has to be greater than or equal to 0. Okay. Siddharth, this is this much okay?
Yes, ma'am. Yes, ma'am.
Okay. Okay. So now r is greater than or equal to 0. Now, can it be positive? That's the question. So suppose r is positive. Okay. So let's say r is some value 6. Okay. Now, so you also in particular assume that there is a value, some z tilde in this cone, such that y transpose z tilde is positive. Okay. So suppose, to show this particular fact, we need to consider some z tilde such that this is equal to 5 or some positive quantity less than r. Otherwise, if you took this as 0, then you cannot show any contradiction. There's no, it is still possible, right? So you can even set r as 0 in that case. If there is no element such that z tilde, there's no z tilde in C such that y transpose z tilde strictly greater than 0, then you might as well set r equals 0 itself, right? So that's why let's assume that there is some element like this, which the dot product with y is strictly greater than 0. Okay, is this basis clear? Why we are taking this as a positive quantity?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, good. So now, so because we considered some such z tilde, which this term is going to be greater than 0. Okay, so now because this is a cone, this C is a cone, so any positive multiple you take of z tilde, you're going to have that element is also going to be in C. Okay, so any alpha times z tilde belongs to C. You can take alpha how much ever large you want. Okay, so now while doing that, if you take, so this is a scalar, right? So alpha times z tilde. So now if you take y transpose alpha z tilde, so this is the new element that we have, and it belongs to C because C is a cone. So now if you take y transpose alpha z tilde, we're going to get this alpha y transpose z tilde. This is just the number. Okay, so something like say alpha is 2 or 3 or something of that sort. Okay, so now, so while doing this, since alpha is free, right, you can take it as large as you want. So at some point, this alpha y transpose z tilde will exceed the value of r. Okay, so to illustrate that, this was the example I took. So y transpose z tilde is 5 and r is 6. Now if I take 2 times z tilde, so what I'm going to get is y transpose z tilde is 5. So 2 times y transpose z tilde, that's going to give you 10. So now that is not less than 6, right? So this is not less than r. Okay, it's not less than or equal to r. Okay, so that's the idea. So any element you take here, if it is going to be positive, you can scale that number. You will choose another element of this number. You can scale it to be large enough so that it exceeds r. So the only way this cannot happen is if R is 0. Okay, so does that make sense?
Yes, ma'am, got it.
Got it?
Ma'am,
Okay.
can you repeat why
Yes.
was y transpose z tilde greater than 0?
Yeah. So let's say that, okay, let's take the case where, there is no z tilde. Suppose there is no z tilde such that y transpose z tilde is greater than 0. Okay. So that means for all, for all elements of, so let's say for all z tilde in C, suppose y transpose z tilde is less than or equal to 0. Okay, so that we have eliminated that because R has to be greater than or equal to 0. So so let us say that for all these cases, let us say y transpose z tilde is equal to 0. Okay, so then you're already done. So you can just set R equals 0. Okay, so now you found this hyperplane, right? So that's what you wanted to prove, that R is 0. You can just set it equal to 0. Okay, so right. So what you're trying to show is that you cannot have this as positive. So for no value of z tilde, you will have y transpose z tilde as positive. You're trying to eliminate that argument. Okay, so that's the reason why you take some value of z tilde for which suppose this y transpose z tilde is positive, right? Right. So Rajneesh, is it
Clear.
okay? Yeah, okay. Any other questions on this? Okay, I think I'll ask a few people. Devansh?
Ma'am, I had one thing like why if we take R as 0, then that means alpha are we taking every time 0, right? There's another option for alpha also then.
Which one? I mean, here. So,
If we take
okay.
R as 0,
So,
then alpha will also have to be 0 every time, right?
not necessary. So, a particular value of alpha for which this is satisfied is, okay, alpha is 0. Okay. Right. But it doesn't mean that, that is the only value. Why do you say that?
We said we claimed that R is equal to 0 and then
Ma'am, I got his doubt. Can I try to explain?
Sure, sure.
Yeah. So if we take R as 0, then that Z transpose times that should be less than 0. And then even if we scale it up, even if we take alpha equal to 10,000, then it will move to the negative side. So it would be scaling up in the negative direction. So that is possible because then it's again less than 0.
I didn't quite get it.
Okay, so I don't know at which point. So is this idea clear that the separating hyperplane is such that you have this relation holds for every point in the set. For every point in the cone, you have y transpose z is less than or equal to r. Is this point clear? So that's what is the separating hyperplane.
Yes, ma'am. This part is clear.
Right?
The you can scroll down the next part that was covered. That is not clear to me. Like when we claimed that R is equal to 0, and we said that R only has to be 0. It cannot be greater than 0, right?
Right.
So,
So
like,
what
when-
we are right. Okay, go ahead. Tell me.
Yeah, so like when we took R as 0, then what I think is like the only possibility for this can be that alpha has to be 0. Because when we saying we can scale it up or down, then we need to have z, like this particular part at y transpose z also to be 0 or less than equal to. But how will that affect it?
No.
I'm not getting.
No. So what we are saying when r equals 0 is, so let's just take some examples. Okay, so let's take a value of r as negative, some r equals -5, r equals 0, and r equals 5. Okay, so I'm just taking 3 examples and let's just see what the statement means. Okay, so what we are saying is there is a hyperplane such that, so let's take R as -5 first. So Y transpose Z is less than or equal to -5 for all Z in the cone. Okay, so this is one thing. Or is it that Y transpose Z is less than or equal to 0 for all Z in the cone? So that is this. If you say R is 0, this is what it means. Now, if you say R is 5, this means Y transpose Z is less than or equal to 5 for all Z in the cone. Okay, so when we say R is greater than or equal to 0, it doesn't eliminate this possibility. Okay, right? So we are not saying that if you cannot have these elements will not belong to. That's not what we are saying. We are saying like what is the best value to put for R, such that this relation is true for everything in that set.
Okay, ma'am. Okay, I thought that we're just eliminating all the negative R values.
No, that's not what we are doing. We are saying
Okay,
that
okay.
if you, right? So we are saying that this R, you cannot put a negative value such that this is true for every Z, because you have the 0 vector which is lying in this set C. Right. So because of that, whatever thing you take here, I mean, there can be some things like this, but this will not be true for every Z in C. That's the idea. Right. You can have some because Z0 is part of the set, and for this value, this particular thing, Y transpose Z, where Z is 0, for this it is 0. So it's not true that Y transpose Z will be less than or equal to some negative value for everything. Okay, so you cannot have this for every element of the set, but you can have some elements for which this is negative. This Y transpose Z can take a negative value, but you cannot have it as strictly positive. That's the idea.
Okay, ma'am. Yeah, I got it. Thank you.
I hope I didn't confuse you more.
No, ma'am. And now it's clear now.
It's clear. Okay, good. Okay. So, any other questions on this? Okay, the rest of you are quiet. Bhavna, what's happening? Is it okay? Is there some confusion?
Ma'am, I got till the hyperplane. We drew a hyperplane. Then actually I lost my internet connection and missed some points. But I joined
Okay.
after the R should be greater than 0 and less than 0. So I got the concept. But I have to review it once.
Okay.
So I
Okay.
got.
Okay. Fine. What about the others? Anushri?
No questions, ma'am.
No questions. I hope it's clear.
Yes, ma'am.
Okay. What about Lakshmi?
It's clear, ma'am.
It's clear. Okay. So I understand like it's, there's a systematic thing, flow of ideas here. So just try to go over this proof once again on your own. Of course, we can again come back to it and, discuss it more. Okay. So, yeah, I think, we have run out of time now. Okay. So what I'll do is, I'll just end with this note, like, so this is this theorem of alternatives that we have here. Okay, so you can have different kind of systems. Okay, you can devise this kind of theorem of alternatives. So either the system is feasible or the others. These are two related systems. Okay, so even if you don't have this x greater than or equal to 0, there'll be some other alternate system. If x such that ax equals b is feasible, then there's another system which is infeasible. Okay, so you can construct such systems using these basic ideas. Okay, it's the underlying thing is mainly the separating hyperplane theorem. Basically construct some convex sets and try to do the separation. Okay, so these things will be useful like when we start linear programs. So my plan is from the next class we'll begin formally looking at linear programs. Okay. All right. So yeah, if there are no questions, I'll stop here. Okay. And thanks a lot for coming. I'll meet you next week. So I'll hang around here for any more questions. If not, thanks.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Ma'am,